All right. Well, guys, is everybody ready for the rain again? I think this afternoon it's supposed to come back, so we'll get this class done and stay nice and warm, and then maybe you guys will be able to go home. I have to stick around all day, so by the time I leave, it's gonna be wet, is what I heard. So we'll see. We'll see how it goes. Anyway, welcome, guys. This is our last class before the Thanksgiving break, so we don't have anything coming up next week. Let me just take a quick minute, and I actually put up a little calendar on the board. If you want to take a picture of this, feel free to do this. You can see we are getting very close to the end of what we have to do for the class. I've actually published all of the homeworks that are left. There's only 3 of them left. So let's just see where we're at on our little calendar here. On Tuesday, I finished chapter 8, and today I'm going to start focusing on to chapter 9. We're kind of skipping section 9.1. It's just a little intro section about systems of differential equations. The real meat of the material starts in 9.2, and so I'll be covering 9.2 and 9.3 today. There was supposed to be a homework assignment due tomorrow night that was based on that, and I realized that since I haven't covered 2/3 of the material that's on that homework, that I should give you a little bit more of a cushion to finish working on it. So this homework for this week's material, instead of being due on Friday, I'm going to let you work on it through Sunday, and I'm going to have some office hours on both Friday and Sunday in case you have questions about it. So it's not a real hard. These 2 sections we're going to cover today, I don't think are super hard, but still, I'll try to be a little bit available if you have any questions on that. So you do need to turn in that homework before we really are officially off for our week of break. So that's right. Next week, guys, no classes at all. I am actually going to be out of state again, so I won't be around. You can always email me during the break, though. If you have questions, if you start doing any studying, feel free to do that. When we come back from the break, we will already be in December, and we only have 2 regular weeks of class left. In that first week of December, I'm going to be covering sections 9.4 and 9.5. Both of those will take us an entire day each. Those are 2 hard sections. They have a lot of material in them. If anybody wants to study them over the break ahead of time a little bit, I certainly have video on that already done. And the only reason I mentioned that is I was down by my office this morning and I noticed that people were already working on the homework from chapter 9, and it's all over the boards outside my office. And I'm like, how did that happen? Oh, well, people are actually working ahead a little bit. So if that's you, if you like to kind of get ahead of the game during this slow week next week, you can do that. Both of these sections will take some effort to learn. And the homework on those 2 sections will be due on that Friday the week we get back. So that's homework number 23. And then the following Tuesday, we have our 3rd midterm. I am going to be doing review sessions before this midterm, just like I did for the 2nd exam. I'm going to tell you about that in just a second. And then on the very last day of class, we have 1 little section. 9.6 is really easy. It's only about 30 minutes for me to go over that with you. And the homework that's based on 9.6 is just 2 problems. So homework number 24 is barely even an assignment. It's just a short little thing. So that shouldn't be too bad. It's really this 9.4 and 9.5 that takes the most time that we'll have to work on. After that, we will jump right into finals week. I believe our final is scheduled for Tuesday. However, I am going to give you some options on this because I have another section that has a final at a different time. I'm probably going to try to reserve a 2nd classroom in case people would like to move their final to Thursday. You will have a choice which day you want to take the final. Some people just want to get it over with at the regular time, but some people, I've seen this in the past, they would like to have a little extra time to study for their final. So that will be an option for you. You can look at your finals week schedule, when all of your other finals are, and what would make the most sense for you. But anyway, I'm going to give you some flexibility about that, just so you know, you can kind of keep that in mind. But yeah, that is our whole schedule for the rest of the semester. I've also pulled up our Canvas page here, guys, because I just wanted to point out that I already have in the files section, like I always do, I already have a resources folder for the third midterm here. So I'm gonna highlight this and go into it for a second. In here is the same old stuff that I give you every single time we have an exam in this class. There are 2 sample midterms again, just like always. There is a review session, and the problems for that review session, I'm going to go over in the review session that I'm going to do. And then there's also just a review packet. Let me open that review packet for just a second. It's already ready to go. I kind of worked on this a couple days ago. And one thing I just wanted to let you know about, so this is regarding our midterm, which is on Tuesday, December 9th. I am going to do review sessions again. They were very well attended when we did that last time. And so I thought, well, if people are going to come, I'm going to do it. So on Sunday, December 7th in the afternoon from 3 o'clock until about 5:30, I'm going to be in this room doing a review session. And then I'm going to do another one on Monday evening. So starting at about 7 p.m. But this room is not available on Monday nights. I figured that out. So I'm going to use that large classroom that I used before that last exam down in the basement, not very far from my office. Pretty much the same review both times, but of course, there'll be little nuances that are different, I'm sure, depending on the questions and so on. Anyway, I'll record those review sessions and send them out. You don't have to go, but if you're able to and want to, I just wanted you to know when the dates and times of those will be with enough notice to kind of adjust your schedule for that. In case you're wondering what that third midterm will cover, it's going to have 4 parts, basically. The last part of chapter 6, this was the sections on kernel and range of a linear transformation. That involved things like onto and one-to-one, isomorphisms, stuff like that. And then we covered eigenvalues and eigenvectors, the whole diagonalization process for non-defective matrices. So that's chapter 7. And then we just finished chapter 8, which was actually 4 sections. We learned the annihilator method, we learned variation of parameters, all that good stuff. And then the material we have not covered yet, which we're going to start on today, is 9.2 through 9.5. As you can see, we're going to cover 9.2 and 9.3 today. And then after the break, we'll come in and do 9.4 and 9.5. Each of these sections would be about 25% of what you need to know for our third midterm. So I'm really giving you it's not for another almost 3 weeks, but I'm just giving you a little heads up now about what it's going to be covering and what you're going to need to get ready for. Just because with the week off next week, some people do like to kind of get their ducks in a row and get ahead of schedule a little bit, and we actually have an opportunity to do that. If you just want to take next week completely off and relax, that's also fine. There's no classes, there's no homework, nothing is due. But this first week back in December will be fairly intense because, like I said, these 2 sections will take a fair bit of work. There will be a homework on them right away on that Friday, and then we turn right around and take that midterm. So just so you know, that's kind of where we're at. Anybody have any questions, Max?
The final, what are the sections that you covered for that one?
The final will be totally cumulative. So anything we covered since day 1 will be on it. However, if you study hard for this midterm, which means you're studying these 4 chapters, you won't have to study these 4 chapters again. There will be a small little bit of new material here, but it's very small. If you study these 4 chapters, keep in mind that within these 4 chapters, you're also doing vector spaces. You're also doing null spaces. You're also taking determinants. You're also doing EROs. All of that stuff is all in here too. So believe it or not, people who work hard to get ready for midterm 3 often find that they don't have to put a massive effort into studying for the final. There'll be a few little things that slip through the cracks, like the stuff at the very beginning of the semester doesn't really come up so much in this material. And inner product spaces doesn't come up in the material so much that we're doing here, but it's not a lot. It's actually not as bad as you might think. So I will guide you on that, of course. Once we get to that point, I'll try to let you know what I think would be the things for the final that you need to review. You've probably already noticed that there is a folder. Let me go back. There is a folder for the final as well, final exam resources. So there'll be something there that you can also use to kind of get ready for that. Okay, so I just wanted to spend 5 or 10 minutes here at the start of class today getting you oriented for these last 3 weeks of regular classes, plus our week off and our finals week. That's kind of what we're looking at between now and the end of the year. Any other questions? Okay, but either way, the biggest priority is for next week is for you guys to get some rest, enjoy time with your families, and kind of get rested up for the big push that we'll have in the first half of December. So that's a big priority too. Okay, yeah, Yakov?
I know you said you would want to get a second option for the final.
I am going to do that.
So
yeah.
You don't know like what time.
You know, I didn't really prep very well for this because it's so far off still.
Right.
I believe that this final is from 9 to 11 on Tuesday, and I can't remember what the other one was. I'll look it up and I'll let you know. Yeah, I should do that. Yeah, that's for sure. I know the other one is on Thursday. I just can't remember. I think it might be from 3 to 5 in the afternoon. I can't remember for sure. I'll have to look that up. Okay, anything else, guys? All making sense? Just have to take it one day at a time, believe it or not. It's less than 30 days to go, less than a month. We're going to be totally done with everything. It goes by so fast. Okay, well, if there's nothing else for now, I would like to start today by covering 9.2 and 9.3. These are not too bad, I don't think. I think that this should be pretty sensible. I gave you on Tuesday some motivational examples of real world problems where this stuff comes up. And in the case of a system of differential equations, I used the 2 tanks with the chemicals pouring in and they're kind of going between the 2 tanks. Most real world problems, guys, involve more than one unknown function. So your unknown functions consist of maybe several of them. And I do want to point out that in chapter 8, we were writing our functions usually as y of x. In this chapter, where we're talking about systems of differential equations, you're going to be seeing me use x of t more often. The t can be thought of as time. So that's your variable. Everything is a function of time. But you have several unknown functions here, right? x1 of t, x2 of t, x3 of t, and so on. And you'd like to solve for all of them. And the thing is that these unknown functions are, of course, going to have derivatives. But their derivatives actually depend not just on themselves, but on all of the other unknown functions that are there. So the derivative of x1 depends on x1, but also x2 and also x3 and so on. And there might be some function on the end here, which is b1 of t, which doesn't have anything to do with any of those x's. Just could be some external function as well. So this list of equations is a little bit messy. You can see we have these aij functions in front. Everything is functions of t here, right? And so those are just like coefficient functions in front of those unknowns. So if we hooked up 2 tanks that both had chemicals pouring into them, we would have 2 unknown functions, which would be how much chemical is in each tank separately. But the amount of chemical in each tank would be depending on what's going on in the other tank as well. And you could, if you had some specific numbers, you could actually put these functions into a problem and have an actual real problem for that as well. But this is kind of the generic setup right here. Does this make sense to everyone? That this is kind of this is what a linear system of differential equations looks like, at least first order linear system, which is all we're going to work on. We're not going to be seeing higher derivatives here. It's just going to be the first derivatives, and that's what you have on the left side, the first derivatives of all of these functions. Okay? So far, so good? What do you imagine might be the very first thing I'm going to do with this linear system here? What's the first thing we always do in Math 250B, when we have some system of equations, what are we most likely going to do with it? You know the answer. Put it in a matrix. Put it in a matrix, right? I'm going to try to rewrite this thing in a matrix form. Let me show you how we can do this. So I'm going to rewrite this system in matrix form. So the unknown vectors over there on the left side, I'm just going to lay those out into a column. So x1 prime, x2 prime, and dot, 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 all the way down to xn prime. So we'll just make a single column out of those on the left side. And then if I look at all of the expressions on the right side, what it looks like to me is that we have dot products going on. A11 times x1 plus A12 times x2 and so on and so on. That suggests matrix multiplication. So A11, A12, and so on to A1n is getting a dot product with these unknown functions x1 through xn like that. So if I was to actually multiply this out right now, I would take A11 times x1 plus A12 times x2 plus A13 times x3. It's exactly the terms that I have here, guys, on the right-hand side. And don't forget there are these b's here. So I'm going to do a plus. And in this last column, I'm going to put all of these b's, b1, b2, and so on, down to bn. And let me finish filling out this matrix. We would have, A21, A22, and so on, A2n. And the matrix just goes down like that. And the last row would be AN1, AN2, all the way to ANN. So this is putting it into a matrix notation. I have suppressed the T now. So over here, I wrote of T around everything. Those T's are still here. I'm just not writing them down anymore. Okay, so that's the way it would look. And I'm going to take this matrix form and compress it even more. Okay, that is, I'm going to compress it even more. This column on the left side is actually a vector. So I'm going to write it as a vector with a derivative. So this is just going to be thought of as the x vector prime. And then that is going to be equal to this matrix. I'm just going to call it capital A. And then I have the actual x vector itself, again, without the prime on it. And then the column of the b vector on the right, I'm going to write that as a b vector like so. So here becomes the even more kind of compressed version of this system of differential equations. And our goal with this is to solve for the vector x, right? We're going to try to solve for the vector x. That's the idea here. Okay. Get this out of my way. We're going to try to solve for that vector x in this system here. So far, so good, guys? Everybody with me? Yeah, well, so it turns out that b vector is a little bit of a hiccup in the whole process. It creates some difficulties. So a lot of times we're actually going to be looking at systems where the b isn't even there. All of these extra functions that are tacked on, they could just be zero. So if that's the case, let me just make a definition here. I'll just make a definition. If the b vector, which consists of, b1, b2, and so on down to bn, if that is equal to 0, so if everything here is 0, right? So if the b vector is just 0 and it's not really playing a big role in my system, then the system of differential equations is called, anybody have a guess what it's going to be called? What the word is? What were you saying? Homogeneous, exactly right. It's the same word we use for like everything. It's just called a homogeneous linear system. So if the B vector is 0, then you just have a homogeneous linear system, and the way it would look now on paper would be x prime equals a times x. So if there's no B vector, that's your whole system right there. So if the B vector is not there. Okay? Now, until we get to section 9.6, which is the thing we're going to do like the very last day of the semester. Until we get to that section, we will assume that the B vector is 0. So for most of this chapter, we are not going to consider the B vectors at all. We're just going to assume that our linear system does not involve any external functions on these differential equations. So we're just going to be assuming that the B's aren't there, which means this is what we're trying to solve, and we want to solve it for X. That's the idea. That's going to be the idea. Okay? So far, so good? This is just kind of the background theory in this first part of chapter 9. So you just kind of have to put up with this until we get into the actual practical part of like, well, how do you actually solve these systems, right? So that's gonna come very soon. Well, guys, there is going to be a ton of linear algebra in approaching our goal of solving for X. I love it. I love how everything we've been doing earlier in the semester is going to come back to the surface. If you thought that stuff from chapters 2, 3, 4, 5, 6, 7, and 8 were gone, no, it's all coming back here. And I'm going to start with a little taste of linear algebra right now with the following theorem. And by the way, this might feel a little bit the same way that I sort of started chapter 8, where I had to give you the whole big theory first, and then later we learned the annihilator method and the variation of parameters method, but there was sort of a setup of the whole topic. And there was a theorem in chapter 8 very similar to this. So here's what it says, guys. The set S of solutions to x prime equals a times x. There's my $1 million system of equations again. The set of solutions to this forms an n-dimensional vector space. It forms a vector space. It forms a vector space, and its dimension is n. By the way, what is the n? The n is related to the size of this matrix A right here. So the matrix would be n by n. That's the way I've got it set up in this diagram here. It's an n by n matrix. You might notice that the matrix is always a square size matrix. So in chapter 9, we're only going to be seeing square matrices. If I have square matrices, I can do things like take determinants. I can find eigenvalues and eigenvectors. Like much of the material we learned earlier on can be used in this context. Okay, let me actually try to prove this for you. I'm going to write it down because, hey, we have to remember how to show that something is a vector space. It has to be closed under addition and scalar multiplication, right? So let's just check that. Closure under addition. Okay, so let's just suppose that both x and y are elements of S. So in other words, both x and y are solutions to my system. So thus, what this would mean, okay, we can write down what that means. If x and y are in S, it means they solve my system. So that would mean that x prime is equal to a times x, and y prime is equal to a times y, right? Those two equations would both be true. If x and y are in S, then both of these systems would be correct equations. Now, ultimately, what I want to do is I want to add x and y together This is closure under addition. So I have to add the two vectors together, the x and the y, and see if it's still in S, right? So let's just maybe do that over here. What happens when I take x plus y? Now I want to see, is it still true that if I plug it into my system, I get a solution? So let's take the derivative of this, and let's just see if it is equal to a times x plus y. Okay, let's check it out. Well, we all know that derivatives respect addition, right? So I can break this up as x prime plus y prime like that. And the x prime, we already were given that that is equal to a times x. And the y prime, we were given that that is equal to a times y. And anybody have a knee-jerk reaction what they want to do here? Pardon?
Factor out the A.
Factor out the A, exactly. There's a matrix A in front of both terms, right? So we can just pull it out in front like that, times the quantity x plus y. Well, that's what we wanted, right? So x plus y prime is equal to A times the quantity x plus y. Well, so that checks it. So x plus y is an element of S. You guys remember doing these proofs? This is in chapter 4. Back in chapter 4, we had to do these proofs. They were always like two parts. The closure under addition part, which is kind of what we've just illustrated here. And then in a minute, I'll show you the scalar multiplication. So far, so good? Everybody with me? Let's check the scalar multiplication. Closure under scalar multiplication. Can we remember how that gets formatted? What do I usually call my scalar? That's usually k, exactly. So let's let k be a real number. That's a scalar. And then I have to grab one of the vectors from above. I'll just say, let x be as above. That's usually the way I wrote that. Be as above. So we have our scalar k, and then we're going to let the x be as above. And I need to check what happens when I take k times x. So let's do that right here. I don't have a lot of room, but I think I have enough. It's actually not very long. I'm going to take the derivative of k times x, and I just want to see whether this is still going to equal a times k times x. So this is the guy that I'm plugging in on the left side, and I just want to see, does it end up giving me what looks like on the right-hand side. So let's just check this out. What do you suppose I'm going to do first here, guys? It's so abstract, like I can't even really take the derivative because I don't know what anything is in here. But of course the derivative is here, but what do we actually see that's inside of that we could do first?
Can we take the K out?
Take the k out. Yeah, the k is a constant, and whenever you do derivatives, right, derivatives respect scalar multiplication, so you can pull the k right out. I'm going to do that first. K times, and then we have x prime. It's going to look like that. Now, I already said that the x was as above. We already know that the x prime was ax. So I'm going to just replace this with ax right there. So the x prime just gets changed to ax. Now, this is not exactly what I want, because what I really want is for the a to be way out in front, and then to have my whatever my vector is after that. So in the way it's written now, the a is kind of sandwiched in the middle of this whole thing. And normally with matrix multiplication, we learned that you cannot just freely switch the order of anything with matrices. However, when it comes to a matrix and a number, which k is just a number, that is okay. I can actually switch the a with the k because k is actually just a number. So I'm going to rewrite that as a times the quantity of k times x. And guys, this is what I wanted. The vector kx prime is equal to a times the vector kx. That little calculation shows it, so let's just wrap this up. So k times x is an element of S. So that checks that part off. So this was the first thing, guys. We actually do have a vector space. We do have a vector space. And this is only going to be true, of course. This is only going to be true for our homogeneous system. If we try to go back to the non-homogeneous one, if we try to go back to this one right here, I claim this one isn't even going to pass the zero vector check. If you put in 0 for x and 0 prime, which is also 0, this plus b is not going to work, right? You're going to get 0 on the left and b on the right, and they're not going to match up. This non-homogeneous system doesn't even pass the zero vector check. That's the problem. But this one does. And not only that, this passes the zero vector check and is actually closed under the operations, which means that you do have a vector space. What is so great about that, by the way? The fact that we have an n-dimensional vector space here. Who cares about something like that? Remember, guys, that a vector space always has a basis. And if you can just simply find that basis, then all of the solutions to this system will be spanned by that basis. So you're not just looking through the whole entire universe for solutions to your system. You just need to find n solutions to your system. And if you can do that much, of course, they need to be linearly independent. But if you can find n linearly independent solutions to your system, then you can build all of the other solutions as linear combinations of them. I love that. That's the power of the linear algebra. I have a professor friend over at Fullerton College, and they have changed the way they teach this a little bit now, and they teach differential equations and linear algebra as two separate courses over there. I don't really like it, but they do it. They do use my book though, so I still have to be nice to them. But the thing is that some of those instructors have been complaining to me lately that they're trying to teach this stuff and the students don't know anything about vector spaces because the linear algebra, it was a separate class and they maybe didn't take it yet. So they're in here trying to understand, well, who cares if, I mean, first of all, they don't even really understand what a vector space is. But then they also don't realize that, to solve this system, which has infinitely many solutions, they only have to find n solutions. By the way, n is usually 2 or 3. So you're trying to find 2 or 3 solutions. It's not too bad, right? It's not too bad, but you have to understand the background of the linear algebra to really appreciate that. The fact that 2 or 3 or n basis solutions would be capable of spanning all of the rest of the solutions as linear combinations of that basis. So it's nice that we've learned that stuff because it makes sense to us that this big job of trying to solve this system really amounts to just finding 2 or 3 solutions to that system, which is, of course, the stuff we also have to learn how to do, but at least it sounds a little bit more palatable. Sounds a little more doable. Okay, so let's keep going. Any questions so far, guys? Let's keep going. This is going to get just better and better, by the way. There's going to be some really cool surprises coming up today. So don't blink, you might miss it. It's really good. It's really cool. I have to, now that I've got myself dialed in, that I'm looking at a vector space and I need n basis solutions, the question of linear independence comes into my head immediately. Like, how am I going to know if my solutions are Li? That's a good question. Let's write that as a question actually for the notes. So here's a question, guys. And we're going to ask the question and then we're going to answer it immediately. The question is, how can we tell if n vector functions x1 of t, comma, x2 of t, comma, dot, 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 up to xn of t How could we tell if we had n vector functions? Right? How can we tell if those are Li? Now, I really want to make sure everybody's understanding that each one of these actually has n functions inside of it. These are vectors now. So in chapter 8, we were doing scalar functions. We had, we would have things like y1 of x and y2 of x and so on. And we actually asked this same question in chapter 8. If I give you a bunch of scalar functions, how do you tell if they are Li? But these scalar functions are not sort of looking the same as these vector functions. Each one of these is like an entire column with a bunch of functions in it. That's why I got arrows on top of those. Those are functions. These are vector functions. Is everybody getting this? There's a difference between chapter 8 and chapter 9 in terms of even what the vectors look like. Okay. Well, can you guys remind me again? If I had n scalar functions, which is what we did in the last chapter, and I wanted to know if they were Li, what was the answer for that? Like, how did we end up doing it? Jose?
Matrix augmented with 0.
Numbers.
I like the first part, when you said the word matrix. But I don't think we did any augmenting with zeros. You're thinking of checking for linear independence way back in chapter 4, when we had like polynomials or vectors in Rn. You would be absolutely right. We would lay those vectors into the columns of a matrix. We would augment it with zeros and do our EROs. But more recently, I'm actually just thinking about basically just last week. Like when I had n scalar functions and I wanted to know if they were Li, how could I mean, if there's only 2 of them, then I just have to see, are they scalar multiples of each other or not? But what if I had more than 2? If I had n scalar functions, y1 of x, y2 of x, y3 of x, and so on, what did I use to determine whether they were Li? I'm looking for one word, and it starts with a... That's it. Starts with a W. The Wronskian. We used the Wronskian. Do you remember that? We took the determinant. I'm just scribbling here for a second. You don't need to write this down. But we took the derivative on the second left row, right? It went all the way across like this. Everybody remember this? Right? You go all the way down until it's a square matrix. You try to find a value of x that makes this not 0. As long as you could do that, then your functions were Li. That was the Wronskian. That was what I called the W test that you guys just learned last week in the chapter 8. Okay. So the question is, what is the answer here? Because now I'm in a different context. I'm not looking at scalar functions. I'm looking at these vector functions. Each one of these vector functions fills an entire column. It turns out, guys, that the answer to this question is that there is a different kind of Wronskian. And so I'm going to have the same answer here. And we're actually going to have a W test that's going to be basically the same thing. But this Wronskian is different than before. It's not going to be the same as before. The Wronskian that we had before, we took derivatives down the matrix and so on. This Wronskian actually is easier. This one is actually easier. What is the definition of this Wronskian here? W of x1 vector, comma, x2 vector, comma, dot, 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 up to xn vector. And this is all of t. So everything that you see will have t's in it, in theory. And the way you're going to do this, guys, is you are going to take the determinant of a matrix. So far, that's the same as the Wronskian that we learned in chapter 8. But the difference here, my friends, is that we don't have to take any derivatives. All you have to do is lay these vectors into the columns exactly as is. there's no need to actually take any derivatives. It will already be a square matrix. Just as is, it will already be a square matrix. So that's the good news. It's actually an easier Wronskian than the one that we learned before. Okie dokie. So far, so good, guys? Questions here? Everybody's so quiet this morning. I'm like super stoked. Guys, this is the punchline. What is this, week 13? So all that work we did for 12 weeks is going to start paying off in chapter 9 now. I've already seen vector spaces come back. Now I'm seeing determinants come back. Linear independence is coming back. And if you wait just a few more minutes, eigenvalues and eigenvectors are coming back too. So there's just so much that's being brought back together in this section. So I get a little bit excited at the end. So maybe I've stolen all of your energy from you, and I have like 30 people's worth of energy right bubbling out in me because I just get so excited about this part of the class. But anyway, stop me if you have any questions. Okay, we're gonna have a W test for this Wronskian, just like we had for the one in the last chapter, and it actually reads almost exactly the same. So let me write it down. It's just the theorem here, and then we'll do an actual example. I realize so far it's been kind of theoretical, but I will get an example up for you here in just a minute. Let's state this theorem, and again, this is also what I like to call the W test, but it's a slightly different Wronskian than what we had before. So if there is a value of t, let's say t naught, such that w of x1, x2, and dot up to xn of t naught is not 0. So if I can find even one value of t that makes my Wronskian not 0, then it's exactly what we had for our W test before. The set of x1, x2, and so on up to xn, that set of functions is Li. It is Li. That is our W test. Now in group work 12, which I did during our Zoom class a week ago, I actually proved the W tests that we had in chapter 8. So there was a previous W test for scalar functions. This now is the W test for vector functions. And the proof of this, I guess I'm going to write down a proof. Just because it only takes a minute. It's not very hard. How do I show? How am I going to show that these functions here are Li? I'm going to do the usual definition. I'm going to assume that these vectors cancel out in a linear combination. C1 times x1 plus C2 times x2 and plus plus Cn times xn is equal to 0. I'm going to assume that. And does anybody know what I'm going to try to show? That the constants are all equal to 0. Very good. So that's the definition of Li, is that if these vectors cancel out in a linear combination, the only way that could have happened is if these constants are all 0. So I'm going to show you that, and it's only a couple of lines. Okay. The first thing is we can rewrite this little equation here. So we can rewrite this as the following. What we can do is I'm going to go ahead and write it down, and then I'll have us look at it and make sure we all kind of believe it. We can put these x's into the columns of a matrix here, guys, and we can multiply it by this column of C1, C2 up to Cn. And then this would be equal to 0, 0, 0, 0, 0, 0, 0. All zeros. Right, so we can rewrite it like that. You know, this sometimes takes a little bit of thought. You know, if I have a matrix, you don't need to write this down unless this is really something that would be helpful for you. You know, if I have a couple of columns here, and then I have C1 and C2 expressed as a column on the right, if you actually multiply this out, right, if you do the matrix multiplication on this, you'll get C1 plus 2C2, and then on the bottom row, 3C1 plus 4C2. Well, you can rewrite that as C1 times 1, 3 plus C2 times 2 and 4. C1 times X1 plus C2 times X2 can be rewritten as columns of X1 and X2, right, multiplied by the constants C1 and C2. This is simply a rewrite. I'm not doing anything here other than rewriting the left side of that linear combination, the left side of this equation. Okay? But this matrix that I have now written right here is literally the matrix that the Wronskian takes the determinant of. And if that determinant is not 0, what do you guys know about a matrix whose determinant is not 0? Invertible. It is invertible. Exactly. So this matrix in front is invertible, which means what? Cancel it, get rid of it, basically. And what will you, if you get rid of this matrix here, look at what's left. All the C's are equal to all the zeros, which is what somebody told me we need to show. Right, exactly. So let's just write that down. That's all that's left. That's all there is to this, guys. Nothing very heavy here at all. It's just, the point is, for the value T naught, the matrix X1, first column is X1, second column is X2, all the way up to Xn is invertible. So we can cancel it by using the inverse. We can actually cancel it and leave ourselves with, well, basically C1, C2, and dot, 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 up to Cn is equal to 0, 0, 0, 0, 0, 0, 0. And that checks linear independence for us. That is exactly what we wanted to be able to say. Sweet, 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 sweet. Awesome stuff. I saw a whole new board here. Let's just do an example of this W test. Just try one out for a minute. So let's just try maybe an example here to practice with. See if this makes a little bit of sense. So I'm going to ask you this question. Is the set of vectors, and the first vector is going to be t plus 1, t minus 1, and 2t, comma. And then my second vector is going to be e to the t, e to the 2t, e to the 3t. And then my third vector is going to be 1 sine of t and cosine of t. So I'm making 3 vectors here. Just to be really clear, right? The first vector is x1, the second vector is x2, and the third vector would be what I'm calling x3. So I have 3 vectors in this example. And the question is that Li? Are these vectors Li? That is the question. Let's think about it for a minute. So I'm just going to use my little W test. So remember that in chapter 8, we had to like take derivatives of stuff to make our Wronskian. But here we don't have to. This is already a 3 by 3 matrix if you just think about it. Just lay all of these columns into this matrix. This is exactly what we're going to do. We're going to build that n by n matrix, and then we're going to take the determinant of it. So for the solution, let's write down I'll just call it W here. W is equal to the determinant of, and then I just literally have to make this 3x3 matrix where I just lay these vectors into these columns. I don't even have to take a derivative. So that's why when I said that I think this Wronskian is actually easier than the one we learned in chapter H, it's because you just write it down. You don't have to actually do a derivative. Now, what does my W test say? It says if there is a value of t that makes that determinant not 0, then my vectors are Li. So all I have to do, guys, is try to think about plugging in a number for t so that this determinant would be not 0. That's what we want. And I mean, you could just try and use the arrow method and leave the t's in here, but it's going to be a mess. You're going to get 6 messy terms with that arrow method. I would prefer to take a gamble and try to evaluate this at a particular number. Does anybody have a nice number for t, or I'll call it t naught now, that we could at least try? I would always try to, as long as 0 is in the domain, I would always probably start with that. Yeah, let's just do that. Let's just put in 0 everywhere we see a t. So if I go back to my matrix and I plug in 0 everywhere for t, e to the 0 is 1, so I get the first row is just 1, 1, 1. And then when I put in 0 on the second row, I have negative 1, 1, and 0. And then on the third row, when I put in 0, I get 0, 1, and 1. Like that. This looks a lot nicer for me to deal with than that. Let's just check it out. If I use my little arrow method, the first arrow gives me a 1. The second arrow is actually going to give me a 0. The third arrow is going to give me a negative 1. Then I go the other way and I subtract 0. And then I subtract 0. And then I subtract negative 1. So you see, we're still using the stuff from 6 chapters ago, right? We learned this arrow method 6 chapters ago. It's a long time. And if you add up all these numbers, the point is it is not 0. It is not 0, and that's good. That's a good thing. Makes me happy. So what that means is that my functions are Li. The answer is yes. By the W test. So by my, excuse me, by the W test, my original vectors are Li. Does that make sense? Just a couple quick things here. What if I had gotten 0 here? If I plugged in this guess, if I just tried to plug in 0 for t and the determinant was 0, what would you probably do? Yeah, you would try a different value of t because maybe you just got unlucky. Remember, this just says if there is a value of t. It doesn't say it has to work for every value of t. So if the first value of t that you try doesn't work, just try a different one. If you try 2 or 3 or 4 values of t and you keep getting 0 every time, so you lose every time you're losing, you're not getting the W test to pan out. After about 3 or 4 values, I might start to wonder, are these vectors really Li or not? Okay, let's do one more example where the vectors maybe are not Li and see how we would maybe get to the conclusion and come up with the right answer. So let me do one more example. Because you're sort of probably sitting there thinking, well, how many different values of t am I supposed to try? If I've tried 4 or 5 values of t and I keep losing every time, right? At some point, I've got to kind of maybe come to a reckoning that these vectors are maybe not Li. So let's just try one more example. I'll make this one a little easier. So is the set of the first vector is just going to be t and t cubed. And then the second vector is going to be 5t and 5t cubed. Is that Li? Now, you might already, just looking at them, know the answer here, because I've made it so obvious, sort of. These are only two vectors, and when you have only two vectors, right, this is x1 and x2. Do we have a fast way of figuring out linear independence when there's only two vectors? What is it, Keone?
They're scalars of each other.
Exactly. If these two vectors are scalar multiples of each other, then they're not Li. And you can see that they are. So the second vector is just, so we actually have a fast answer, no, and we can just say since x2 is 5 times x1. So I can see that they are scalar multiples of each other and say no. But let's just pretend for a minute that we didn't notice that. Let's just pretend that we didn't notice that. And so we come down here and we just start playing the game with the Wronskian. Let's say we didn't notice that they're scalar multiples of each other. So we just come down here and we start doing the W thing, kind of blindly. Well, how does that work again? Well, we're going to take a determinant. And how do we do the determinant? I just erased it, but it's on your notes. It's basically just put these vectors directly into the columns of your matrix here. So you would just do that. Now, if you follow my advice from a minute ago, is, oh, try to plug in a value of t. So if I try to evaluate this, I'd probably start with 0. If I do that, well, then I'm going to get the determinant is 0, 0, 0, and 0. And so this is 0, and so then that's not what we wanted, right? So my advice to you a minute ago was, well, okay, if the first value of t doesn't work, try another one. So we could try another one. Let's try again. So we'll take the same exact matrix here. What would be maybe the next value of t that would be an obvious one to try?
42.
1. Did you say 42? I think for me it was going to be 1. Okay, I would probably try 1 for t naught. And if I plug that in, well, everywhere I see a t, I'm putting a 1. Well, then I get this matrix. And I do this determinant as, oh, well, shoot, that's also equal to 0. Okay, so we're losing, and we can try another value of t, and we get 0 again. And we try another value of t, we get 0 again. The question is, at some point, we need to catch on. It's like, you know what? I don't think it matters what value of t I plug in. It's never working. So what you can do, if it's never working after 3 or 4 or 5 tries, is you can say, I wonder if I could just do this determinant without plugging in a number for t and just see what it comes out to be. So in general, in fact, let's write it over here. In general for this one, guys, in general, right, the W here is just the determinant of, so t and 5t and t cubed and 5t cubed. So instead of plugging in a number for t right now, what I would recommend doing is just, if you're starting to get suspicious that it's not going to work, I would just do everything with the t in there. So t and 5t cubed minus 5t times t cubed. I'm just using the AD minus BC formula. And what you notice here, guys, is actually that it doesn't matter what t is. Any value of t is going to give you 0. No matter what you do, even if you try for the next 500 years to plug in a number for t, you will always get 0. And that means that there does not exist a t naught that makes my Wronskian non-zero. And so we would then conclude that no, these vectors are not Li. Of course, here, I just have to say they're not scalar multiples of each other, but keep in mind, this could be a 3x3 system. If it's a 3x3 system, then you can't use the scalar multiples reasoning anyway. So in that case, this is what I want you to do. If the vectors are LD, right, so that is actually the conclusion here. If these vectors are LD, the way to really convince me is to show that your W would always be 0 by leaving the t in it and just working out the math that it cancels out. I think there's one like that on the homework for Sunday, this next homework assignment, where you have to leave it in terms of t. Okay. So far, so good. I have just one definition to write down and then we're gonna take a 10-minute break. Actually, we're gonna be done with 9.2 and 9.3 already. It's really not that bad. So let me put one definition here and then we'll call it good. So definition, actually it's sort of two definitions, but they kind of go together. So I'll just write them down together. So if you have, here's the definition, guys. If you have this set x1, x2 up to xn, and if those vectors are Li, if that set is Li, okay, then, sorry, I need to say one more thing. And xi prime is equal to a times xi for each I. So again, I have solutions to my linear system and they're all Li and A is n by n. Then these solutions are a basis for the solutions to our system. But there's another word that mathematicians use, and it's called a fundamental set of solutions. So then we call this set x1 and x2 and so on up to xn a fundamental. It is called a fundamental set of solutions. And so we have a fundamental set of solutions. They're really just a basis. It's just a basis. So I'm not really, it's not necessary to have this new terminology, but it does get used. If we build a new matrix, guys, called capital X of T, whose columns are just these vector solutions, x1, x2, and so on up to xn. If we just make that matrix, so what we did right here, we made the matrix right here. This would be, for this example we just did a few minutes ago, this would be the capital X of T, just this matrix. And that matrix is called a fundamental matrix. So this is called a fundamental matrix for x prime equals a times x. That's right. It is a fundamental matrix for our system. Technically, its columns are the basis vectors that solve our linear system of differential equations. Pretty cool. So, and by the way, this will be invertible because the columns are Li. Right? Anytime you have a matrix whose columns are Li, then that matrix, assuming it's a square matrix, which this one will be, this will be an n by n matrix, guys, same size as A itself. N by n matrix, and because it's got columns that are Li, well, then it is an invertible matrix. That was one of our, again, results back from chapter 4. Using a lot of the vector space theory here. So I think I've kind of done everything. I've done everything except one thing, which is I have not explained to you how you come up with the x1 through xn in the first place. If we have n linearly independent solutions, we're going to be able to span our entire solution space for our system and write down the general solution. Beautiful. Nothing else to it. The question is, how do you come up with those solutions in the first place? And it turns out, quite unexpectedly, I was shocked when I took this class and I learned that somehow it has to do with the eigenvalues and eigenvectors of that matrix A. So you're probably wondering, that seems kind of out of the blue. Where is that eigenvalue, eigenvector theory going to come in? Well, if you'll just give me 10 minutes to take a break, well, give yourselves 10 minutes to take a break and hold you in suspense, my usual cliffhanger style. In 10 minutes, I will show you how that works and why the eigenvalues and eigenvectors are actually the answer to the story of coming up with these solutions. It's a beautiful thing. Let's take 10 minutes, guys. Go ahead if you want to stretch your legs and get some water, some fresh air, whatever. Let's do that, and then we'll pick things back up.
Like I know every concept, that's me time to definitely and understand.
Are all of your other professors giving you guys exams this week? Yeah. Last week?
Yeah.
I think a lot of people are giving tests this week because before the break, so maybe that's why people are tired. Get some better lighting. How you guys doing? Good? Not too bad. I'm looking forward to taking a little break next week. You good? I'm gonna go do, I've never done one before, but there's gonna be like a turkey trot. You guys heard of that? You go do like a little race in the morning. That way, I guess the concept is so you did your exercise, so then you can go eat like this huge meal. So we'll see how I do. I'm not usually like a big time runner type person. I mean, I have done some jogging, but I won't be real fast. I'm more of a hiker. I go out and I hike at kind of a moderate pace for like 10 hours straight. But I'm not so much like a sprinter. So we'll see how this turkey trot goes. Welcome. What's that? Oh, it's over here. Okay. 2 people?
Right.
Just have here.
Oh,
Oh, I already picked those up.
So of the. It was all like the functions. I didn't like. It's like. But I just like, I don't know, how did I have to like the problem with that on my YouTube, like these things too.
I don't know what I did. Yeah.
This one guy.
I was worried.
You should always.
I was worried too. That's why.
Yeah, when I was enrolling.
Yeah. But I don't.
How'd you do?
And one of them, but the one that went by central.
What was the average?
Again. Mechanics were December.
Damn.
It's just something that my friend did. We didn't let me go.
I'm still in final 7 months.
And I was looking like, oh, I. Stuff like.
Like, but actually, have to know.
And I emailed him.
Yeah. I have consideration.
And I emailed him.
And you should post this.
Yeah. I'm glad that that means.
And then went home, and then the meeting.
I feel like it was like.
That's always there.
All these emotions are not connected to GT7. So I actually have to learn these. That's just so I watched me here. Just like yeah. And I'm gonna throw. Cause I'm taking nothing for that spot.
And then I went back to the email.
Eventually.
I was like, oh.
You would, he put that, he had that guy.
There's a day, you know, I see him.
Yeah.
On the- I was like, oh, and then he did, in the middle of the meeting too, so. He's clutch it, so I got that class.
Definitely would be that.
I like that.
Unless you.
Like, I wanted to submit, like, a visit for my thing. But I couldn't find it online. Like, I don't know how to really get to it, so I just emailed them, I was like, oh. I'm looking for employment, what is your thing with them, like, and he's like, you send me, see what, and then, like, 5 minutes later, he sent back, start chief one time. Yeah, he just like did it on the spot. I was like, oh, like, thinking so much. Telling him, did me, he's actually to go.
It's pretty cloudy though. Oh, so we're. That door propped open, maybe that'll help a little bit. It's cold. I know, it's freezing in the hallway and it's hot in here.
Group work, there was 14.
Oh, I have a high snap score. Like double yours. COVID. And I barely use it now. Were you studying? My friend. Just like videos. Like the videos like are worth like twice as much or like 3 times as much. So like we would just send videos back and forth like all day. What's your time for? Mine's 1.2 days. Huh? I know it would be 2. There's a girl from my high school who has like 5 minutes.
You know what they do?
Or 4. I feel like million is like honestly not that crazy. If you've had it, it's like since 2016. Really? Yours is only
It's just never
no,
retired, do
since
they?
2017. I think yours would be astronomical.
That's when you
I'm
know that person really loves their job.
Once a day.
Probably not
Going
doing
up your
it.
30 count. It's like your 30 count.
Well, as a professor, 23 years, I was a grad student for, this is my 24th year. I was a grad student for about 6 years, so it's about 30 years since the first time I was ever standing in front of a student. Yeah. And I do love my job, but my problem is I have all these other things I want to do too. So I don't think I'm gonna go to 94. I'm actually, I'm 51, so I
94.
probably if I take it. Yes. We'll see. As long as they let me, like, being able to teach once in a while in Zoom really helps, because then I can like still take some trips, and so. I'm trying to like figure out how to like both be a professor still, but also without giving up the job, but then be able to do a fair bit of travel too. That's kind of the challenge. Oh, in person, way better. It's way better for the students, it's way better for me. But I also have my personal ambitions, which have nothing to do with teaching. So I have to figure out like, what's the happy medium. Yeah. Like last week was perfect because we had a holiday anyway on Tuesday. So I didn't feel like it was so terrible. And the material last week wasn't that crazy. So I was like, I think we could handle it for that time. But like, I had also thought to myself, I could have taken this week off too. Because technically I'm allowed to do that. I could have said I'm gonna do this whole week of Zoom as well, and then be gone to Thanksgiving. I could have been gone for like almost a month and been like overseas. But then I thought, that's not gonna be so good. Like, at that point, it's like, you haven't seen me for weeks, like, it's hard to stay motivated. So,
I feel like I learned way less.
when you're in Zoom.
Yeah.
Yeah, exactly. I mean, it's not just because it's maybe harder to learn the material, it's just also harder to be disciplined and stay focused on tasks.
And everything's distracting at home.
You have distractions, yeah, exactly. No, COVID was a rough time, trust me. I had so much trouble getting students engaged at that time themselves. But once in a while, I think it's doable. Also, the first week of the semester, when I wasn't here, it was the same thing. It's like, nobody's gonna come to office hours. It's like nothing really that pressing happening. So I did a little extra personal stuff during that time.
I understand it. I'm fine.
But yeah, we'll see. See how it goes. Let's see here. All right, guys, I think I might go ahead and pick things back up here again, if that's all right, and we'll get started. In a few minutes, we're gonna actually do the group work today at the end of class. That's gonna be kind of what we wrap things up with, and that group work is still chapter 8 stuff, so it's kind of the stuff before today's class. But I would like to actually take just about 10 more minutes of lecture time to kind of put a nice little wrap up on what we've been saying so far today. We've got our homogeneous linear system here. I hope everybody's dialed in on this. This is mainly what chapter 9 is about, solving this system. And we now know that the solutions of this system, they form an n-dimensional vector space. That was our theorem from a little bit earlier. So the question is, how can we get our basis vectors? How can we get our basis of n linearly independent solutions to this system? That's really what this question is asking. How can we find our spanning set or our basis for the solution space? So it turns out, I kind of already gave you a little bit of a hint about this. The answer, it turns out that it has everything to do with the eigenvalues and eigenvectors of A. Remember that A is an n by n matrix. So it's a square matrix, and so we can talk about its eigenvalues and eigenvectors. And let's suppose that lambda and B is an eigenvalue, eigenvector pair for capital A. So suppose we actually find the eigenvalues and eigenvectors of A. And we have this pair right here. I'm going to consider doing the following thing, guys. I'm going to build an x of t right now. And the way this is going to work, guys, is we're going to take e to the lambda t, and we're going to multiply it by v. So let's just write that down in a box. This is going to turn out to be pretty important, this expression here. But what I'd like to do right now is I would like to take the derivative of it. Okay. Oh, by the way, can somebody remind me, let's just do this over here on the side before I take the x prime of t. Does anybody remember what the most important equation is that relates the eigenvalues and eigenvectors? I kept talking about it being the most important equation in chapter 7. Anybody remember what it said? Like 2 weeks ago, maybe 2 or 3 weeks ago. So we were doing eigenvalues and eigenvectors. It is for sure going to be on your next midterm. We had theoretical problems about it. Anybody want to give it a shot?
It's like A minus that version. Or the other one.
Not quite. No determinants. You're thinking of the characteristic equation.
That's-
You guys are on the same wavelength. There was an equation even before that.
A times
Yeah, yes, that's it. AV equals lambda V. Guys, you write this down on your midterm. I'm gonna light up my face and give you points for that. So AV equals lambda V. Yes, thank you. Okay, I'm gonna need that in just a second. So let's just kind of keep that on the side. Let's come back over here. If I build x of t like this, I'm gonna try and plug it in on the left side and on the right side of my problem and see if it works. Let's take the derivative here. So then x prime of t is equal to, so if I take the derivative of this with respect to t, of course, the derivative of e to the lambda t is going to be lambda e to the lambda t, and this vector is just a vector of constants. When you take derivatives of constants, they just kind of come along for the ride when they're multiplied in. So this is the derivative of the x of t. And now, guys, you can probably see why I wanted to remember the most important equation in chapter 7, because I do see lambda times v right here, and I can replace it by a times v. This exponential, let's just throw it into the front for a minute. So I'm going to put the lambda v next to each other and keep the e to the lambda t in front. So let's write down e to the lambda t, and then I'm going to put a v here. Okay. Sorry, I'm going to write down 2 more lines, guys, here. So if you have to stand up in the back to see all of this, feel free to do that. What I'm going to do is I'm going to remember that A is a matrix and e to the lambda t is a scalar. You can switch the order of those. I can put the a in front, and I can put the e to the lambda t with the v. And what do you have? You could just go down to the next line of your paper, but I don't have any more room, so I'm just going to write it over here. This is a times x of t. Wow. Wow, look at that. X prime is equal to ax. It works. It satisfies this system. The left side is x prime, and when you crunch the calculation out, it comes down to a times x. So if you're looking for solutions to this system, guys, look no further than the eigenvalues and eigenvectors. If you just make an eigenvalue eigenvector pair, you can build this guy right here, and you'll have a solution. You'll have a solution. Now, there's a bunch of potential pitfalls here that we're going to be talking about after Thanksgiving. One of them is the eigenpairs, as we've already seen this, they can involve imaginary numbers. So if you had imaginary lambdas and v's, then your solution here is, again, kind of nonsensical. It's like, how do you take e to an imaginary power? It doesn't really make sense. We're going to have to figure out how to get the imaginary numbers out of it. That's coming after Thanksgiving. The other thing that can go wrong is that we need n of these. We need n of these, and they need to be Li. So our matrix would need to have n linearly independent eigenvectors. Does every n by n matrix have n linearly independent eigenvectors? I'm putting you guys on the spot about chapter 7 again today. You didn't come in here thinking this was going to be an issue. Do you remember that a matrix could be defective, potentially? What did that mean? If a matrix was defective, some eigenvalues didn't pull their weight. In that case, you did not get n linearly independent eigenvectors. So you wouldn't have been able to make n of these. And you need n of these in order to be able to write down the general solution. So if the matrix is defective, I also see some potential problems over here. So if the matrix is defective, or if the eigenvalues and eigenvectors are complex numbers, we do have some issues. But if the matrix is non-defective, which is really what this next section is about, 9.4, I said I was going to cover it after Thanksgiving, and I am, but we're going to start right now, just giving a quick preview of it. And in section 9.4, we're only gonna look at the non-defective scenario. Okay, so again, I'm basically only gonna give you a 5 minutes on this right now. Okay, but this will be a nice little segue into this. If A is non-defective, then we have n linearly independent eigenvectors. That's what a non-defective matrix is. And let's just call them V1 and V2 all the way up to Vn. In the non-defective case, you would have n of these, and there is a lambda that goes with each of these eigenvectors. Let's call them lambda 1, lambda 2, all the way up to lambda n. Okay, and so we can form n solutions then. Let's do it over here, actually. We can form n solutions from those n eigenpairs. Okay, so the first solution, I'll call it x1 of t, is going to be e to the lambda 1 t times v1. That's my first solution. Coming from my first eigenpair, we've already verified that that will be a solution. That's what this calculation shows. If you take an eigenpair and you build that guy, it will solve my system. Okay, and then I have a second solution, which is x2 of t, and that would be e to the lambda 2t times v2. And we just go dot, dot, dot. We have n of these. The last one is xn of t, which would be e to the power of lambda n times t times vn. You would have all of these. By the way, we would want to make sure that they are Li. I do have n solutions. I have found n solutions to my system here. This is the verification that they really are all solutions. But we would technically want to know that they are Li, and I can easily show that to you. What's my test for Li? The Wronskian. We had our new Wronskian today. Let's just check that real quick, the W thing. Let's just check this guy out. What's my Wronskian? Well, that's the determinant of the matrix that I can make by putting my vectors into these columns. So e to the lambda 1t v1 goes in the first column. The second column is e to the lambda 2t times v2. And we just go dot, dot, dot. We lay these vectors into the columns of that matrix. Now, what's happened here is that each column vector was multiplied through by a scalar. The scalar being the exponential. The e to the lambda t is a number that's scalar multiple. So this first column is really v1, but with a scalar multiple of it. The second column is v2 with a scalar multiple of it. Do you guys remember back when we did determinants? If I multiplied a row of a matrix through by a scalar, what did it do to the overall determinant of that matrix? Like if I have we did EROs. Remember we were doing EROs and we were like, well, what are the effects of on the determinant? If I took a matrix and I multiplied the first row through by 7, what happened to the overall determinant of the whole matrix? Do you remember that? So if we have A and then we multiply a row by K to get B. Does anybody remember how the new matrix determinant was related to the old determinant? Sure you do. You remember it just got multiplied by K. Whatever that scalar was that you multiplied through by, the determinant got multiplied by that scalar. So if I multiply the first row of a matrix by 7, the determinant goes up by 7, a factor of 7. Okay, I hope I'm not speaking Greek here. This is chapter 3. Okay, we've seen a whole bunch of, right, we're on chapter 7, chapter 3, chapter 4, all the earlier chapters are coming back. Do you notice that? There's almost nothing that hasn't been touched today. I guess I haven't done an ERO for about 5 minutes now, so that somewhere along the line we'll probably do those too. Actually, to find the eigenvectors and eigenvalues, we have to do null spaces, which involves EROs. It's all here, all here. Anyway, my point is, I'm getting a little sidetracked. My point is these scalars, they can basically be pulled out of this determinant. Because that's essentially what happens when you multiply a determinant through by a scalar. And I do admit that in this context, we are scalar multiplying the columns instead of the rows. Like over here, we were doing row operations, but it actually doesn't make any difference. Because after all, if you transpose a matrix, there's no effect on the determinant. And so pulling scalars out of columns of one matrix, you might as well just imagine that you transposed this thing and then pulled those scalars out of the rows and then transposed it back. But guys, quick question. Can e to anything ever be 0?
No.
Nope, that's not 0. This one, same thing, not 0. This one, same thing, not 0. And now what am I left with over here? This is a bunch of vectors that are Li. In a matrix where the columns are Li, that determinant cannot be 0 either, my friends. This whole thing is not 0. My W is not 0. These are Li. They are Li, and there's n of them. And it's an n-dimensional vector space of solutions. So you know what? Your general solution is right in front of you. The general solution, I'll write it here. This is the last thing we really need to do to get at least a preview of 9.4. Let's write down the general solution. This is so nice. X of t equals C1 times e to the lambda 1 t v1 plus C2 times e to the lambda 2t times v2 plus Cn times e to the lambda n t times vn. That would be your answer for the general solution to this system. And you want to know what? 95, I'm going to say maybe even 98% of the work in coming up with this answer is just finding the eigenvalues and eigenvectors. Actually, once you have found the eigenvalues and eigenvectors, all you're doing here is assembling it into this expression. And you're done. You're absolutely done. Normally, I would stop now and do an example, but I think, unless anybody has a question, I'll just leave it at that for now. We'll come back to this in 12 days when we reconvene after, and we'll actually do some examples. We do have those issues. We do have those issues. What if A is defective? This isn't going to work. I have to give you a reason to come back after Thanksgiving. So if it's a defective system, this isn't going to work. The other situation it's not going to work so well is if there are imaginary numbers in these eigenvalues and eigenvectors, then this will be something that your boss will not like. It will not really make sense because you can't really you can't touch and feel or even graph or plug numbers into a function where you have imaginary values on top of an exponential. Just doesn't make sense. So we have to figure out how to extract real solutions from something like that. So there's issues here. I'm not saying that we're done with everything, but at least you have a real good idea of where we're going with this now. This is the strategy. So, okay, guys, all I want to do for the last 15 minutes today is have you take the group work that is in front of you. This is changing gears completely back to chapter 8. I'd like you to think about annihilators and variation of parameters again and try and solve. One of those is an annihilator problem and one of them is a variation of parameters problem. See with your group if you can work one or both of those out in the next 15 minutes. and I'll come around and give you a hand.